talk about where the p-test comes from. So we're going to start in this video by answering the question, for what values of p is this series convergent? And this is exactly the rules of the p-test. So essentially we're going to derive where those rules come from. And then we're going to use it as a guide to answer a spin-off question, for what values of p is this thing convergent? We're going to use a similar strategy. Okay, so assuming we don't already know the rules of the p-test, we would consider this series and say, okay, let's do the integral test. The integral test says, consider the integral from 1 to infinity of 1 over x to the p. If this comes out as a convergent improper integral, we're convergent, and if it's divergent, we're divergent. So even though we don't know what number p is here, it's just kind of like a fixed mystery number, we can get pretty far in the problem before we have to decide very much. Okay, so the first thing I'll do to start computing this improper integral is replace the infinity with a letter and limit that letter towards infinity. I'm also going to rewrite 1 over x to the p as x to the negative p, because I know I'm about to do an antiderivative, and that's a more helpful formatting. Now, we're faced with our first choice here. So what the antiderivative of this is depends on if p is 1 or not. Right, so off to the side, we'll say, okay, if p equals exactly 1, we are looking at the limit as b approaches infinity, integral 1 to the b, and this would be x to the negative 1, which is 1 over x as the original function. So then we would have an antiderivative of ln absolute value. So this is just one single case of the problem because it has a separate antiderivative. So this would be ln of b minus ln of 1. And this limit does not exist. This limit goes off to infinity. So p equals 1 is going to get lumped in with the diverge category. We've kind of just computed it as its own case, decided diverge. So whatever we decide p needs to be convergent, we're going to exclude 1 from that answer. All right, so then that brings us back to, if p is not exactly 1, then we're using the reverse power rule for this antiderivative. So we keep our limit out front, and we would have 1 over negative p plus 1, x to the negative p plus 1, evaluated from 1 to b. And remember, these two are x values. So in the next step, when I do plug, plug, subtract, they're just going right here, and the p stays just the letter p. All right, so we keep our limit for one last step. 1 over negative p plus 1, b to the negative p plus 1, minus 1 over negative p plus 1, 1 to the negative p plus 1. Okay, so we know that powers of 1, no matter what this exponent is just going to be 1. So all of this we can kind of drop out, and we just have 1 over negative p plus 1. So whatever p is, this is just some number. Okay, so when we're considering the limit, we are really focused in right here. And this is where it really matters exactly what kind of number p is. And it has to do with this exponent here. So this is just some number out front, so it's not going to change whether the limit exists or not. So if we have b getting very, very large, and it's raised to an exponent, there's two different things that could be happening. So if negative p plus 1 is a positive number, so it's greater than 0, then as b gets very large, these powers of it just get very, very large, right? So it's like the limit of b squared or b cubed or b to the 10. Those all just go off to infinity. And we would end up in a DNE situation, which means we would have concluded divergent for the integral and the series. But if this is a negative exponent, right, like b to the negative 2, negative 3, that's really a denominator. So if negative p plus 1 is negative, less than 0, then this limit equals 0. because you have like 1 over b squared, 1 over b cubed as b gets very, very large. So this would put us in the convergent scenario. So this negative p plus 1 less than 0 is the key to the whole thing. We're only going to be convergent if this is true. And if I wanted to include the 1, I would make this an or equals 2 here, but we know p equals 1 is not part of this category, so we don't have to worry. All I need to do is solve for p by adding p to both sides. So we'll do plus p, and we get 1 is less than p, aka p is greater than 1, which is usually how we say it. So as long as the p value here is greater than 1, it's a convergent improper integral because we get a limit. And that would mean that this series is convergent as well. All right, so let's use that same integral test strategy for the second example. For what values of p is this thing convergent? We say, okay, let's go straight to the integral test. We'll consider the integral from 1 to infinity, and I'm going to switch all of these n's into x's to make it continuous. And again, x is the actual input variable, p will just sort of be a mystery number for us. To compute or start computing this improper integral, I'll take out the infinity, put a letter, limit the letter. Same steps as the previous example. So I have 1 to b, x squared, x cubed plus 1 to the p dx. All right, and this one has kind of an extra step compared to the previous example because this doesn't just have one big antiderivative rule, or I guess 2 that we had up top. This is going to be a u substitution. So no matter what, we're going to have to do u equals x cubed plus 1. That makes du 3x squared dx. I'll swing that 3 over. So x squared dx, that's this part with this part. That'll be replaced with 1/3 du. So altogether, this integral would be u to the p power, whatever that p power is, times 1/3 du. And I'm not bothering to convert the bounds because I'm going to bring it back to 1 and b, but certainly you could convert the bounds as well. Okay, so we again have the split, right? So if this exponent is exactly -1, then we would have a separate antiderivative. So we'll split this into 2 cases and kind of investigate, all right, if it's exactly -1, what's going on? And then if it's anything else, what's going on? So we've got our 2 cases here. P is not -1. P is -1. Okay. So if P is exactly -1, we just have one specific case, right? So then we can actually put a -1 in there. So then we'd be looking at the integral of 1 over u times 1/3 du. And that would give me 1/3 ln absolute value. Bring back the limit step. So b approaches infinity. 1/3 ln absolute value, x cubed plus 1, 1 to b. And then when I plug, subtract, this limit will not exist, and I'll kind of exclude this from the final answer just like before. 1/3 ln b cubed plus 1 minus 1/3 ln 1 cubed plus 1. And this limit goes off to infinity. So dne, so this would put us in the divergent situation. Okay, so p equals -1 will not be part of our answer because they're asking which ones give you convergent. All right, so let's go back to the rest of the cases, which is every number except for that. So if p is not -1, then this is a reverse power rule problem. So then the antiderivative, and I'm going to keep this limit right away. The antiderivative would be 1/3 times reverse power rule here. So we'd have 1 over p plus 1. And then my u is x cubed plus 1 raised to the p plus 1. Notice that the way that this problem was constructed, the p is this original exponent, whereas up here, we started with 1 over x to the p, so really negative p was the exponent. So that's why this antiderivative looks a bit different here, because we're just treating p differently. All right, and we're doing between 1 and b. So I'll do my plug subtract. Keep the limit on the outside. You could factor out the 1/3 all the way, or even the 1/3 times 1 over p plus 1. You could factor them all the way outside the limit if you want to, but it's not mandatory. B cubed plus 1 to the p plus 1 minus 1/3 1 over p plus 1. 1 cubed plus 1 is 2, so I just put that 2 in there, p plus. Okay, so there's a lot more going on here, but we're still going to roughly think about it the same way. And for the limit, I really care about just this part, right? The only actual occurrence of b in this whole statement is right there. So this is just a number, this is just a number. So this is really deciding if this limit exists or not. And we have the same situation as before, right? Where we know b cubed plus 1, as b gets very large, is just going to get very large. So if it has a positive exponent on it, this limit doesn't exist. So if p plus 1 is positive, then this just gets bigger and bigger forever, right? Because it'll be b cubed plus 1 squared or cubed or whatever, and that just gets large. But if this exponent is negative, then this is really 1 over a power of this, and your limit will be 0. And that would put us in the convergent category for the integral and respectively the series. So this is going to be the key to our answer for this problem. P plus 1 has to be less than 0. And if I subtract the 1 over, that would mean P has to be less than -1. So my final answer for this would be that P has to be less than -1. And I know I'm not including -1 itself because we said that belongs in the diverge category with these guys here. So as long as P is strictly less than -1, this will be a convergent series.